with operationally, how do you apply Archimedes' principle? So, from an operational perspective, the idea of Archimedes' principle, as I was saying on Thursday, is actually really straightforward. So, the best way to imagine that is, suppose you have water and you put some solid, some heavy solid in the water. Let's say a piece of rock in the water. So what Archimedes' principle does is the rock occupies a certain volume, right? That's the rock has a certain volume. So if you took the volume that the rock occupied, and if you imagine that that volume was instead occupied by water, and calculate the weight of that volume of water that the rock displaces and subtract it from the weight of the rock in air, that gives you the weight of the rock in water. So that's really the basic idea behind Archimedes' principle. So in other words, for example, when a ship floats on the sea, the ship displaces a part of the ship that's underwater. It displaces a certain amount of water. Amount of water, the volume of water that the ship displaces. Take that volume, multiply that by the density that gives you the mass, multiply that by g. That is the weight by which the ship's actual weight in air is reduced. So all you are really looking for is to make sure that the actual weight of the ship minus whatever weight the displaced water gives you is actually the weight that you are dealing with. So when we float, for example, in a swimming pool, that's exactly what's happening. So the amount of water that our body displaces is essentially the weight of the water, that volume times the weight of the water that's essentially taken out of our weight, and that's why we float. So the basic idea of Archimedes' principle is very simple. Whenever you encounter a problem, I want you to remember that is the way it's to be done, and then all kinds of details and confusions typically that come up in the calculations of students tend to fade away. Okay, so be very sure about this, and if you have any questions, feel free to ask me about how you'll operationalize it. I gave you one problem in the homework that's due due today on this. So I might throw in a few more in one last set, just to give you some amount of practice on that. The last thing that we did was we finished up on last Thursday with Bernoulli's equation. And Bernoulli's equation is actually an energy conservation equation that as I mentioned. The difference is that in this case, it's energy conservation for a fluid. And the properties of a fluid are somewhat special, and therefore the equation is slightly different, at least in the way it appears, than a normal energy conservation law where you just take the kinetic energy plus the potential energy is equal to the total energy. Here it's a little bit different, but otherwise it's the same. So let's say, for example, that if you have a pipe, and the pipe goes through a couple of different levels, maybe let's say for simplicity, 2 levels, and the thickness of the pipe, let's say, varies. So this is your pipe, okay? And let's say the fluid, whatever the fluid may be, water, something else, enters here, and the fluid leaves the pipe at this point here. So any kind of pipe is characterized by a cross-section. So let's say the cross-section here is A1, the cross-section here is A2. The velocity of the water here as it enters is V1, and the velocity of the water here, let's say, is some different number, V2, right? We assume that the density of the fluid doesn't change. for simplicity, and therefore we can say the density of the fluid is basically a constant. So this may not be the case if you have a gas where the density may change, let's say, but let's assume that is not the case and we hold the density to be constant. So, but the other thing that will be special is that because it is a fluid, the pressure levels here and here may not be quite the same. So we must now allow for a different parameter which we haven't really dealt with before, and that is the pressure level, because as you know, water pressure varies, right? So water pressure, if you are going to take water from the ground floor to 30th floor or something, then you have to arrange for special ways of getting the water up there, because water is not naturally going to rise up the pipes of a building. So, and one reason why water wouldn't rise up is because the pressures are different. The pressure is lower above, higher below, and stuff like that might be getting in the way. So what is Bernoulli's principle telling us? So before we write down Bernoulli's principle, we call this level of height y1, let's say, and we call that level of height up there y2, let's say. All right? So just to go over, you have a fluid going from y1 to y2, pressures are p1 and p2, and the velocities are v1 and v2, and the density of the fluid is rho, and rho is deemed to be at this point a constant. Okay. So Bernoulli's equation basically says the following. It says 1/2 the density times the velocity square, okay, plus the potential energy density actually, and I'll tell you in a moment. In this case, let me call it y, because I'm using y, plus the pressure. These three quantities end up being a constant. That's all that Bernoulli's equation really tells us. So density is, as you know, definition of density is mass over volume, right? So this piece here is half mv squared, which is kinetic energy over volume, and therefore this is kinetic energy over volume, which we call kinetic energy density. So anything divided over volume is typically written like that, kinetic energy density. Basically that's what it is, kinetic energy over volume. Now you know that mass times g times y is what we have seen for a long time as potential energy, right? Excepting here, it's rho. So mass over volume, that's what rho is. So therefore this term here is basically giving you what you would call potential energy density, meaning potential energy over volume. So this term also has to do with volume. Pressure is an interesting term. You know that pressure is defined, we define pressure as force per unit area, right? That's how we define pressure. But if I multiply above and below by distance, some distance d, then this becomes a volume, this becomes work done. So in other words, pressure is actually nothing but energy over volume also. So therefore, it's an energy conservation equation, excepting it's written in terms of being divided by volume. So Bernoulli actually realized this, and that's why this equation is very important. And you can therefore relate what's going on in this pipe by saying 1/2 rho v1 squared plus rho g y1 plus p1 must be equal to, in this case, 1/2 rho v2 squared plus rho remains the same, g y2 plus p2. And you see P1 minus P2 is going to give you Y2 minus Y1 with all the constants that go with it. So in other words, if you take away all the motion and kill off the V term, you recover Pascal's principle. So Pascal's principle, which is something that we worked with, is actually embedded here as well. So this is really the guts of Bernoulli's equation. And I gave you an example of blood pressure, for example, on Thursday. So as far as our blood pressure goes, the reason, for example, our blood pressure drops when we exercise is basically because when you go for a run, let's say, your heart's beating faster. If your heart's beating faster, then the blood flow through your arteries is faster. So if the blood flow through your arteries is faster, then the kinetic energy goes up, right? So when you go for an exercise, the kinetic energy of the blood that's flowing through your arteries goes up. Let us say the Y level doesn't really change. You have a certain amount of pressure. When you are relaxed, you're retired and vegging out by the beach, your heart's not doing as much work, so your kinetic energy goes down, your body is not very happy with it, your pressure goes up, all right? So it's basically that idea. So when you exercise, our bodies essentially naturally tend to lower the blood pressure because the kinetic energy goes up. It all comes out of Bernoulli's equation. When you have a low pressure system, let's say in the atmosphere, a low pressure system would typically mean, if this part is held fixed, that you have strong winds. If you have a high pressure system, it typically means winds have slowed down, all right? So this is basically the idea that Bernoulli's equation gives you. It's very special, it's very important, and therefore I want you to make sure that you get the concepts. Any questions on this? Think about it. I mean, this is something in which there are a whole bunch of applications that you can think of just from hearing the weather person to what have you, right? So, and it pertains to your bodies as well. All right. So if there are no questions on this, I'm going to move on, and I'm going to talk about what can be characterized as there are 3 chapters that go under the general banner of heat and thermodynamics. So this is a big subject, it's an important subject that actually really, really seriously affects us. And clearly this is not something that we are going to do in great detail in a course like this, but we touch upon it because we introduce the basic concepts. So I wanted to kind of introduce the basic concepts to you because it is, like I said, it's very relevant to the sciences in general. So, talking about pressure and all that, whenever we talk about heat and thermodynamics, one of the things that we are talking about is we are talking about a system, whatever that system is, solid, liquid, gas, mud, muck, whatever you want. And we are also talking about stuff like temperature. Now, we all know what temperature is, although I haven't given you a precise physics definition of temperature yet. But we know what temperature is. Naively, we know what temperature is. It's a measure of how warm something is or how cold something is. We know that the sun is very hot. The sun has a certain temperature. We know that, Buffalo is a cold place. So on a winter day, Buffalo has a certain temperature. We have some naive understanding of what temperature is. But what is temperature in a real sense, in a physics sense? Basically, temperature is a rough measure. It's a global measure, if you will. It's an averaged measure of the kinetic energy of the molecules that make up a system. Okay, that's what it is. So in other words, let's just take something simple, such as the air in this room. I don't know what the temperature is, but let's assume it's 30 degrees Celsius. So, well, that'll be too hot actually. Maybe it's about 20 degrees Celsius. So if it's 20 degrees Celsius, that's a certain unit of temperature, of course. But more importantly, that 20 degrees Celsius is related to the average kinetic energy of the air molecules that make up this room. Now you can say there are all kinds of air molecules. We have light molecules, we have heavy molecules. Are all of them moving at the same speed on average? No, of course not. There is a distribution of speeds, right? Some are moving faster than others, some are very sluggish. There are all kinds of speeds involved. But if you average out, and you know how to average, then you will get a mean kinetic energy of the molecules that make up this room. And that mean kinetic energy is directly tied to the temperature of this room. So we know very precisely what temperature is, although it is a quantity that is imprecise at some level because it's an averaged quantity. However, we can still be quite precise when we talk about temperature. Let's say I take a container. I'm going to do an experiment here, a thought experiment, not a real experiment. This is a container, and I stuff some gas inside this container. And very soon I'm going to ask you a question, so get ready for it. And now I take a pressure gauge, and I stick this pressure gauge in the container so that I can measure the pressure of the gas. And let's say this pressure gauge gives me some reading, and I can measure the pressure of the gas. And you know what pressure is. Pressure, as we just discussed, is force per unit area, right? So in other words, if you were to measure the force exerted by the gas molecules as these molecules hit each and every wall, there are 6 walls. Force, yeah, 6 walls. So you will get a certain pressure. And this pressure gauge measures that pressure. Now you go and measure the room temperature, let's say, and this temperature T, for now we'll call it T. By the way, temperature is always denoted by capital T. Never denote temperature by small t, because small t is reserved for what? Yeah, time. So capital T is temperature. So you measure the temperature, let's say, and you figure out it's 30 degrees Celsius or 20 degrees Celsius. Now I tell you, let's cool this down, put it in the fridge. The fridge is, let's say, at 0 degrees Celsius. And I ask you to check the pressure. So do you think the pressure would be higher or lower? What does your gut tell you? You have a gut, right? Anybody else want to venture out, stick your neck out, and object to that? Or come on, what do you think will happen, Taylor? Repeat the question. That's a delaying tactic. You take this container and you put it in the fridge. What will the pressure gauge give you? Will it give you a pressure reading that is higher than the pressure reading in normal conditions like in this room, or will it be lower? Who said it's higher? Okay. Vivek said it's higher. What do you think? You don't know? Higher. Why would it be higher? See? He has really opened a can of worms. A bottle of water, if you freeze it, it indeed expands, right? So you don't really want to be so stupid as to put a bottle of water in the freezer and expect nothing interesting to happen. At least Buffalonians shouldn't. Now, but I should also tell you that actually it will be lower, and water is the weird one. All right. So water is the weird one in the sense that when you freeze water, it is not the same as almost all the other materials we know. It turns out that when water freezes, there is actually a volume expansion compared to its liquid state. But most systems, when it freezes, there is a volume contraction, because what happens is that if you think in terms of kinetic energy, the molecules don't have that much energy because it is cooler. Okay? Or in other words, cooler means the molecules have less energy. Whichever way you look at it, less energy of the molecules is tied to being cooler. In fact, in this particular case, if I stick this guy in the fridge, you will see that the pressure will start to fall ever so slightly. So your intuition based on water alone therefore gives you an expectation that is not right, which is why I was asking these questions, because we all have these ideas and thoughts, and sometimes it's based on our observations, and observations are correct, but when you extrapolate that observation to something else, it may not be applicable. And this is a classic example, because water is indeed so anomalous, but we have water everywhere. Water is all around us. So it turns out then that if I lowered the temperature by sticking it in the refrigerator, then the pressure actually in general would fall. Let's leave a complicated system like water out. We are talking about very simple systems here. You can think about air. All right, air is complex enough. You can think about a simple gas like hydrogen gas, for example. It's the lightest guy in the universe, right? You can't get lighter than hydrogen. So this system therefore has this problem. So now suppose I actually make a plot. I put temperature along the x-axis, and I put pressure along the y-axis. And I'm actually plotting pressure versus temperature in this box that I have made. And this, by the way, is 0 degrees Celsius, just by choice. There is nothing profound about what I'm doing here. So let's say, for argument's sake, that at a certain temperature, my gas has a certain pressure marked by that star. And as I now lower the gas, this pressure now starts to go down. And most gases won't cause any trouble at 0 degrees Celsius. So it turns out that if you actually do the experiment, you will smoothly come down to the 0 degrees Celsius mark. Well, for Buffalonians, going below 0 should not be a big deal. So you say, okay, fine, I stick it out in the winter, and the temperature continues to fall, the pressure continues to fall. But now you have to ask yourself some questions. A gas, when you make it sufficiently cold, can become a what? Right. A gas, when you make it cold, can become a liquid. Right? So we now have to find a gas that does not easily become a liquid. So let us say, for argument's sake, we have found such a gas. And there are gases like that. So, by the way, this is not exactly a straight line. It has become a little crooked, but it's actually a straight line I'm trying to draw. So let's say we found the right kind of gas that doesn't become a liquid. And now we run into another hazard. When you make it real cold, forget about liquid, it could actually become a solid. And there are gases that can go directly from the gaseous state very quickly, quote unquote, in the solid state. So we now also have to make sure that we have found that special gas that doesn't become a solid. Question is, can we find that? Well, we'll deal with it very soon. But now you see you are actually running into a problem as you lower and lower the temperature, because the pressure can't go below 0. Pressure, as I said, is the average kinetic energy of the molecules, which is half times mass times average velocity squared. Mass cannot be negative. Velocity squared sure as hell can't be negative. So your kinetic energy can't be negative, which basically means that in this case your pressure must be either 0 or more than 0. Mathematically. For it to be 0, all motion must cease, right? Because if you have any motion, then you have a little bit of velocity, and immediately that means that the pressure is non-zero. So we have now run into a situation that if we did everything correctly, we made sure our gas didn't become a liquid, we made sure that the gas didn't freeze, we made it very clear in our heads that the pressure can't be negative, pressure at most can be zero, and pressure zero means that all motion must have stopped. We have set all these conditions. Imagine what a complicated, expensive experiment that would be. And physicists do these experiments for very, very interesting reasons, and I'll tell you. I'll tell you in a minute if I don't forget. So it turns out then that you can actually traverse this regime if you are a sufficiently good experimentalist, and if you have the right material and the right laboratory conditions to do that. And finally, what will happen is that you will reach a temperature where pressure will become as close to zero as possible, and you can't go any further. In other words, there is an absolute temperature T equal to zero. Well, let me not say that yet. There is an actual temperature T. Let me now call this T in Celsius. Tc is T in Celsius, because that's what we could write Tf in Fahrenheit, but let's say Tc in Celsius. There is an absolute temperature T at which the pressure goes to zero. Since pressure can't go below zero, I can't go any cooler than that. It's physically not possible. That's what this plot, this set of arguments is telling us. And this temperature is known. It is actually minus 273.15 degrees Celsius. So nowhere in the universe, mind you, you can have a temperature that is colder than minus 273.15 degrees Celsius. That is the absolute lowest possible temperature you can reach anywhere in our physical universe. You can't go below, because pressure can't be negative. So nature therefore gives us a particular temperature scale, and this temperature scale is called the absolute temperature scale. And the absolute temperature scale has T equal to 0 as the starting point. And this T equal to 0 is minus 273.15 degrees Celsius in our Celsius scale. So if somebody is telling you that he or she has experienced or know of something at less than minus 273.15 degrees Celsius, you know that person is not telling you the truth, because it's simply not physically possible. So what we now say is that we call this the Kelvin temperature scale. So Tk is therefore the temperature in the actual Celsius scale plus 273.15. That's what we define as our new temperature scale, all right? And it's called the absolute temperature scale. It's very, very, now I told you why, I gave you a sort of cryptic answer as to why this is very interesting. It turns out that when you get to this regime, when you get to, incredibly close to this T equal to 0, all motion is about to cease. But what motion is about to cease? All thermal motion is about to cease. In other words, all motion that is tied to the presence of kinetic energy is about to cease. However, that doesn't actually mean that all motion per se ceases. What that means is that there are still quantum mechanical effects that might lead to some motion. And these quantum mechanical effects actually have turned out to be very, very important, and we can probe them in great detail in the modern times, in the last 20, 30 years or so, to the extent that we literally can figure out the number of vibrations, the number of times electrons go around a nucleus of an atom with great precision and so on. Now you might wonder, why is it very important? Well, it's very important because that becomes one way of defining the next generation of super accurate clocks. So you'll hear the word, if you Google up, you'll find the phrase atomic clocks. Atomic clocks are studied in that regime. And atomic clocks are the new standards of time in the world. Now you can say, why do we need such an accurate clock? Well, guess what? If you don't have a very accurate clock, even something like your GPS system will begin to crumble. Because your GPS system that you would use on your phones and in your car actually needs general relativistic corrections. So Einstein's theory of general relativity is built in to the GPS systems that you and I use. So the measure of time, measure of space in these systems that we take for granted have to be incredibly accurate. And if you are thinking that the errors might be small, you are wrong. Your errors actually can be quite large, even on Earth itself. Earth has a very significant curvature, and all those effects start showing up if these corrections are not built in. So space and time measurement accuracy is a very important cornerstone of science as we do it, cornerstone of current day engineering, and cornerstone of current day precision science, which is very, very important. So this whole low temperature problem and pressure having an absolute lowest point is very real. And usually experiments are done with systems like helium. There are various isotopes of helium that are used that under special conditions can be taken down very, very close to the absolute 0 point. All right. So clearly then we know that temperature is a very important thing. We have an absolute low of temperature, but we also touched upon the fact that when we cool something down, the gas becomes a liquid, the liquid becomes a solid, and so on. So what is very, very interesting about heat and thermodynamics are these quote-unquote phase changes. Phase changes. What's a phase change? A phase change, by phase, we mean phases at the simplest level. These are the gaseous phases, liquid phases of materials, solid phases, and so on. And by the way, these are actually far from simple. Just to give you an example, I often have brought up the issue of climate change and global warming. One of the things that have really messed up our understanding of these phenomena is the fact that ice has a whole bunch of phases. We think about ice as the solid phase of water, but that's actually super, super simplified. The last time I checked, and this was a long time ago, 2001, the number of phases that I saw were something like 8 or 9. I think the actual number of phases of ice, that means water in solid phase, is way more than that now. And each of these phases, by the way, are distinct, and they have their own properties that are not exactly the same. So when we melt ice to liquid, each of these phases actually come into play. It also depends upon the conditions under which the ice is at and so on. So because we brought up the issue of ice, I thought I would mention this. It's very interesting. So anyway, what is really bizarre though is that if I think about the gas phase, so this is a high temperature phase. So let me put down a high temperature. Okay, that's where I start. And let me now put down low temperature. So let's say I am starting off at high temperature with a certain gas and slowly cooling it down. Then this gas phase, as I cool it down, will eventually become a liquid phase. And then if I further cool down the liquid phase, it will actually become a solid phase. All right. So if I actually lower temperature, so I say lower temperature by the sign, I will go from a gas phase to a liquid phase to a solid phase. And likewise, if I raise temperature and go like this, from a solid phase, I'll go to a liquid phase to a gas phase. Now, one of the things that comes into play immediately is this a reversible process? And the answer is maybe, may not be. In some cases it is, but in many cases it's not. Yeah, certainly. Basically, a plasma phase is like a fluid phase, right? And the main thing about a plasma phase is that the charges play a very important role. Here we are considering systems where the atoms are charge neutral, okay? But in a plasma phase, that simplification is taken away. So you have to consider the charges as particles. And you also typically have temperatures fairly high, which means that the charges can actually have strong interactions, which is what makes the plasma phase more difficult. But at the same, and there are other phases as well, besides the plasma phase. But I will just stick to the phases that you run into at the simplest level for those molecules that are charge neutral, okay? Just to keep things under control right now. But there is something very interesting. So one of the things is that as I cool down, as I heat up, the issue of whether this is reversible. Now, I will not get into the issue of reversibility in great detail. By reversibility, I mean I go from the gas phase to the liquid phase to the solid phase, and solid phase to the liquid phase to the gas phase, whether these two phases at a given temperature are uniquely defined. That is what I'm asking. So the short answer is, for some materials it is uniquely defined, for some materials it is not uniquely defined. All right? So for those materials, it is where when you fix the temperature and the pressure and what have you, you will get a unique phase of the system. They show what we call continuous transitions. I will not get into that in detail. Where that is not the case, they show what we call discontinuous transitions. So what are these transitions? So this is another very interesting and bizarre thing, actually. The transition aspect of it is as follows. How does one go from a gas phase to the liquid phase? How does one go from a liquid phase to a solid phase? Does it happen bit by bit? Does it happen abruptly? Or some combination of that? So it turns out that there is almost as much richness there as you can imagine, all right? But at the simplest level, the change from a gas phase to a liquid phase happens at one unique temperature. At the simplest level. That's typically what nature gives us. It happens at one unique temperature. We know, for example, that by and large, water would become ice at 0 degrees Celsius. We know that, right? And that is true. Now, if you change the pressure to high or low, that temperature would change. But under normal temperature and pressure, we know that 0 degrees Celsius is a special temperature. This thing holds up in other materials as well. So as you go from gas phase to the liquid phase, this temperature, therefore, turns out to be a unique temperature. And we can denote that temperature for simplicity as TB. This can be the boiling point of the liquid in this case. And the liquid to solid, of course, let me move this around a little bit. Draw it here. This is going to be what we would call, likewise, the melting temperature, Tm. So there are two, therefore, unique temperatures where the system goes over from one state to another at the simplest level. As I said, this is not entirely reversible in some cases, in which case this unique temperature may have its own little peculiarities depending upon whether you're going from hot phase to cold phase or cold phase to hot phase. But for now, we'll ignore that. In other words, we'll deal with what we will call continuous phase transitions rather than discontinuous transitions. But you don't need to worry about that aspect of it. So, before I go any further, let me now clarify. we are only talking about systems in equilibrium. So I haven't really introduced the concept of equilibrium because it's like temperature. It's a primitive concept that one uses. What is equilibrium? So equilibrium can be defined in very mathematical ways, but basically equilibrium means it is independent of any detailed conditions. Independent. So in other words, the state of molecules that make up the gases in this room are not really dependent upon what was going on when this room was built. In other words, mathematically it is not dependent upon the initial conditions that were set. That initial condition information has been wiped off. Okay? That's typical of equilibrium. Equilibrium also means that there is a certain well-known distribution of energies of these gas molecules. We'll not get into that level of detail. Okay, so these are all conditions associated with equilibrium. Equilibrium typically means you can pull off a definition of a temperature which is reasonably precise. So these are things that are tied to the concept of equilibrium. Now, how do you attain equilibrium? That's an important question here. Because suppose I make a system. Suppose I put in a liquid, let's say, okay, so I can give you a simple example. So over here, I shake it up. This is certainly not in equilibrium now, but I let it rest for a while. And if you wait a few minutes, maybe less, this thing pretty much comes down to equilibrium. Equilibrium means that the water molecules here are actually still moving, but there is no global motion that you can actually see in this case, right? In other words, it looks pretty still. But there is actual motion of the water molecules. They're not sitting there. It's not ice. So that's the easiest analogy to attaining equilibrium that I can give you. In other words, when you make a system, you have to make sure that the system gets to equilibrium. If it doesn't get to equilibrium, then everything we are talking about runs into difficulty. So to keep matters simple, we are talking about systems that are in equilibrium. So we have an equilibrium gas, we have an equilibrium liquid, we have an equilibrium solid. That's what we're talking about. So in other words, now if I change the temperature, how do I know that my system gets to equilibrium? I lower the temperature, I raise the temperature. How the hell do I know that my system actually is in equilibrium? Well, I don't really know. So in other words, when I change the temperature, I must wait a bit. All right? I must wait a bit to figure out if the system reaches equilibrium, and if it does, as far as I can tell, only then would the temperature measurement make sense. In other words, we are only restricting ourselves to equilibrium systems. What is interesting though is that this temperature and this temperature for a given material is actually unique. So that's very interesting. So what happens then when we add or take let's say when we lower the temperature or raise the temperature. I've been beating around the bush already on this topic. I'm telling you that if the temperature is high, that means the molecules are moving faster. If the temperature is low, that means the molecules are moving slower. So in other words, as I lower the temperature, the total kinetic energy of the system goes down. So it's an energy. And this energy that goes down as I lower temperature or goes up as I raise temperature is called heat energy. And the amount of heat energy that is raised or lowered is proportional to the change in temperature. So this is heat energy. We all have a certain amount of heat energy in us by virtue of the fact that the molecules are dancing around in our systems. And this, of course, is the corresponding change in temperature. It turns out that naturally the amount of heat energy that will be involved is also proportional to the amount of the material. If I have a very large amount of material, like the ocean, the amount of heat energy that the ocean can hold, or the amount of heat that will be gained or lost by the ocean because of a temperature change will be enormous because the ocean is so massive. So delta Q is therefore proportional also to delta M. Therefore, it's easy to see that delta Q in general, which is the heat energy gained or lost, is proportional not only to the mass involved, but also to the temperature change involved. All right? Delta Q is proportional to mass times delta T. Whenever we have relations like this, proportionalities like this, we convert them to equations, and in this case the equation would be delta Q is mass times, let me write it slightly differently, let me put a constant here, C mass times delta T. So this now becomes a useful equation that allows us to measure for a certain change of temperature how much heat is gained or lost. It's a very important thing, right? So for example, there's an ice sheet that's melting in Greenland. Because of a certain temperature change, you know the specific heat of ice, you know the mass of the ice sheet, and you can figure out how much energy is being absorbed by that ice sheet as it becomes water, and what it will do to the mass of the ocean, because the mass of the ocean will go up and delta Q. These calculations are possible. They're not easy. They're very, very difficult to do. But these are calculations that one can actually perform. So what is this constant C is the question. Clearly, I hope I have convinced you that this is an important constant, right? For any material, this is an important constant because it controls how much heat can be absorbed or may not be absorbed. So this constant has a name. It's called specific heat capacity. And specific heat capacity is measured because this is energy, and this is in kilograms, and this is in degrees Kelvin, because I introduced the absolute temperature scale. So specific heat C is measured in joules. Joule is a unit of energy, obviously, per kilogram and degrees Kelvin. Degree Kelvin is like same as Celsius, excepting that you have this special temperature scale that I introduced. All right. So let us say we want to look at some numbers. So the C values are unique in the various phases. So in the gas phase, in the liquid phase, in the solid phase, etc., the C values are not the same. Okay, so there is a, in this case you would say C for the gas phase, in this case you would say C for the liquid phase, in this case C for the solid phase, for the same material. All right. For the same material, the C values are different. The C values have to be measured. I'll just give you two numbers. For ice, which is of course the solid phase of water, the specific heat of ice, C of ice, is 2.01 times 10 to the 3 joules per kilogram degrees Kelvin. All right. So that's the specific heat of ice. What does it tell you? That gives you a measure of how much heat energy ice can hold. That's what it tells you. And for water, which is far more robust, the specific heat of water is actually much, much larger, 4.19 times 10 to the 3 joules per kilogram degrees Kelvin. So as you can see, water, as you would expect, water can hold a whole lot more heat than ice can. In other words, ice presence in a planet like ours, which is in the Goldilocks zone, is therefore rather delicate. It's rather fragile. Ice can melt easily if our temperatures change by a few degrees. So that's how it goes. Now, as I have told you about gas phase, liquid phase, and solid phase, I've been very careful not to talk about what's going on at the phase transition points, where you go from the gas to the liquid phase, or liquid to the gas phase, or liquid to solid phase, or solid to liquid phase. I haven't told you that. I've just told you that if you raise temperature, then you will gain a certain amount of heat energy, delta Q. If you lower temperature, you will lose a certain amount of heat energy, delta Q. That's what I've told you. But you can only raise or lower temperature if you go back here. You can only raise and lower temperature in these regions, in the regions which exclude the phase transition regions. Those are the areas where we can actually apply this equation. So this is not applicable during phase transitions. Because during phase transitions, I already told you, you have either TB or TM. Temperature is fixed. Phase transitions happen at a particular temperature. So how does it work? It works like this. Suppose you want to make some tea in the morning and you want to boil water in your pan. So you put the water on the stove, right? Turn the stove on, and you stick your finger in up to a point, and you find the water is getting warmer, which is fine. And then after a while, you will see that the water is beginning to boil. And then that beginning to boil becomes a very stable boil. So if you actually measured the temperature with an actual thermometer, I wouldn't recommend it, but if you want to try it, try at your own risk. You measure the temperature, you will find that all the time, from the point it is beginning to start to boil to the point it's in vigorous boil, the temperature does not change. Even though you're giving it more and more heat, the temperature remains fixed because it's absorbing the heat and it's globally becoming a boiling liquid. And as this global boiling sets in, it begins to convert itself to steam. And the temperature of steam will start off at 100 degrees Celsius, but actually will continue to increase. So while it goes through the conversion from water phase to steam phase, during the entire boiling process, this temperature actually will not increase. It will hold fixed until the whole thing has come to a stable, vigorous boil, and then it will continue. So it's very bizarre, but that's what nature does. So that is the reason why I was able to define those precise temperatures TB and TM, because at those temperatures, the whole system is beginning to participate in the transition from one phase to another. Let's say from solid to liquid, or liquid to solid, or gas to liquid, or liquid to gas, whatever that is. All right? So in other words, what I'm trying to tell you is that delta Q equals Cm delta T. That relationship does not work. Does not work. Never try to make it work if you understand anything at all. Don't even go there. It does not work when you are undergoing a phase transition. All right? So you have to understand that the phase transition is very special. So during phase transition, what happens? We'll try to understand that. So during phase transition, what happens is that this delta Q, the amount of heat that will be absorbed, obviously cannot be dependent upon delta T, because there is no delta T. T is fixed. It's either TB or TM. There is no delta T. But it is certainly proportional to the mass, as I said, until the whole system comes to a boil, right? As in my example. So delta Q is proportional to mass. So therefore delta Q, if I want to convert this to an equation, I would write this equation in the following form. This equation would be, let's say, the mass times a constant LV at boiling point. TB stands for boiling point, and this LV is called latent heat of vaporization. Okay, the latent heat of vaporization. It is a constant, obviously. You've got to calculate this, you've got to determine this constant experimentally or calculate it based upon a theoretical understanding. And likewise, when you go to the melting problem, so at T equal to Tn, this would be called the latent heat of fusion. Latent heat of fusion. Okay? So latent heat of vaporization and latent heat of fusion, therefore, are the constants that are going to come into play. So now suppose I asked you, and I will. So in final exam, I will ask you, for example, how much heat is absorbed? Let's say if you take ice and you warm it up, making sure you're hitting equilibrium as you warm it up at every temperature. Let's say from minus 5 degrees Celsius, when it will be very much in solid ice phase, to 120 degrees Celsius when it will be in steam phase, gas phase. So first what you do is you take your ice, which is a solid, and you basically take it in the solid phase using the specific heat of ice in solid phase, which I gave you, C ice here, 2.01 10 to the 3 joules per kilogram degree Kelvin. You go from minus 5 to 0 in the solid ice phase. At 0, the solid ice phase absorbs a certain amount of heat, which has to do with latent heat of fusion out there, to go from ice to water at 0. So this is the next heat it absorbs. Then what it does is it goes from 0 degrees water to 100 degrees water. Again, you have to use specific heat of water, 4.19 10 to the 3. And then you got to convert with latent heat of fusion at 100 degrees from water to steam, and then take whatever steam temperature and heat are involved. So it's a multi-stage calculation, and this is something that I will most certainly ask you in the final exam. So please be very clear that you understand it. All right, let's go to the quiz now. We are done.